This video is part of the series on periodic trends, and it will focus on the trend of atomic radius. When we're measuring the radius of an atom, you can't treat it the way you would treat the radius of a circle. Not exactly, anyway. Because remember, when we talk about the atom and what makes up the atom, we talk about the nucleus. And the nucleus is typically the center. It's considered the center of the atom. And the radius would be the distance from the center to the edge of a circle. Well, because we call what surrounds the nucleus the electron cloud, there is really no definite edge. So when we're measuring an atomic radius, what we do is we look for two identical atoms of an element that are adjacent to one another and find the distance of the nuclei from each other. So if the second picture here is a picture of two identical atoms, the black dot or the black dots here each represent a nucleus. So here are two nuclei of adjacent atoms. The radius of an atom will typically be recorded in nanometers, which is the same thing as saying 1 nanometer equals 1 times 10 to the negative 9 meters. That's how small a nanometer is. Or in picometers. 1 picometer, remember, equals 1 times 10 to the negative 12 meters. That's how small a picometer is. So generally what you'll see recorded as the atomic radius is actually the distance between two nuclei. So the D here represents distance divided by 2. And that is how we get the atomic radius. When we look at how atomic radius changes moving across the periodic table, going down a group, the atomic radius actually increases. So pictured here are group 1 metals. Underneath the pictures of the atoms, you can see a value. It's the atomic radius recorded in nanometers. So notice as we go down the group, the size of the atom increases. Let's consider why that happens. As more energy levels are added, there's less of an attractive force being exerted by the nucleus on those outer electrons, allowing them to move farther away from the nucleus due to that repulsion by the core electrons. The second picture shows you the same atoms, but this time you can see the number of energy levels that each atom has. So lithium being in period 2 has 2 energy levels. Sodium being in period 3 has 3 energy levels. Potassium has 4 because it's in period 4. Rubidium has 5 energy levels and cesium has 6. So notice as you continue to add energy levels, the core electrons, that's where the electrons are that are considered part of the shield. The core electrons shield the outer electrons, the valence electrons, from being pulled in with that attractive force by the nucleus. When we move right to left, okay, so this time we're talking about moving right to left across a period, the atomic radius increases. So let's consider why. It's because as we move this way, right to left, the effective nuclear charge is lower because the number of protons is lower, moving from right to left in a period. So let's take a look at the second picture here. If we just focus on the period 2 elements, notice how they become progressively larger. So why is that the case? Well, as we move left in a period, each successive element, so as we go from lithium to beryllium, from beryllium to boron, from boron to carbon, from carbon to nitrogen, and so on, there is an additional proton in the nucleus. So because we have a stronger effective nuclear charge, the attractive force of that nucleus also increases, pulling those outer valence electrons in closer to the nucleus, reducing the size of the atom. You can say that this trend follows the Snowman Principle. So the Snowman Principle is not a real thing. It's just a memory trick that we can use to help solidify our understanding of atomic radius. Notice when we build a snowman, the base, the bottom, is usually the largest part of the snowman. So that's similar to the way atomic radius increases when we go down a group. So the largest part of the snowman represents the largest atomic radius. And then the smallest part of the snowman, which is the head, is at the top of a group. So also the top part of the snowman. Now, the same trend applies if we knock over the snowman. You got to knock over the snowman to the right, though. So when the snowman falls, the trend still applies because the head falls to the right, and the right side is where the smaller radii are located in a period. So the atomic radius follows the Snowman Principle. Let's do some practice here. Atomic radius, what we're going to do is look at each of the elements in the pairs that are listed and decide which one has the largest atomic radius. So if we're looking at lithium and potassium, find them on the periodic table. Lithium's right here in period 2, and potassium's in the same group in period 4. So which one's larger? Can you see that because potassium is in period 4, it has 4 energy levels, so that's why potassium would be considered a larger atomic radius? Let's look at bromine and fluorine for our next example. Bromine and fluorine are located in the halogen family. And for the same reason that we talked about for lithium and potassium, because bromine is in period 4, it has 4 energy levels. It has a greater shielding effect compared to fluorine, allowing its valence electrons to be farther away from the nucleus. So because of that, bromine will have the larger atomic radius. Next, we have barium and polonium. So because barium and polonium are in period 6, we know that they have 6 energy levels. We can't use the number of energy levels as our determining factor to help us understand which one has the larger radius. So now we need to look at the effective nuclear charge of both of these elements. So if you look up barium's atomic number on the periodic table, you'll see that barium has 56 protons. And then if you look up polonium's atomic number on the periodic table, you'll see that it has 84 protons. So due to the fact that polonium has a greater effective nuclear charge, its nucleus can exert a greater force of attraction on those outer electrons, pulling them closer in because it has so many protons. Barium is the element that will have the larger atomic radius. So in number 1, we have lithium, fluorine, carbon, boron, oxygen, and nitrogen. So I've highlighted all of the elements that we're going to be considering for number 1. So what we're doing is we're going to rank them in decreasing order. So think about what that means, decreasing order. Are we going from largest to smallest or smallest to largest? Well, decreasing means we start with the largest radius and we go to the smallest. So largest will be listed first, and then smallest will be listed last. So let's look for the largest element on this list. Remember, atomic radius increases when you go to the left in a period and when you go down in a group. So because each of these elements is in the same period, we're going to focus on the trend in a period. So lithium is going to be the element with the largest atomic radius. You can list that symbol. Remember, all of these elements are in period 2, so they all have 2 energy levels. So what we need to do is use the effective nuclear charge, the number of protons in the nucleus, to help us decide which valence electrons are farther away. Because lithium only has 3 protons, lithium has 3 protons, its atomic number is 3, and fluorine has 9 protons, a much stronger nucleus. Lithium will not be able to exert as strong of a force on its outer electrons as fluorine will, due to that lower effective nuclear charge. So next on the list is going to be boron. Boron has 5 protons. Then carbon. Carbon has 6 protons. Then nitrogen, 7 protons. Then oxygen, 8. And then finally fluorine. Fluorine being the smallest atomic radius. All right, let's take a look at number 2. We have hydrogen, we have potassium, lithium, sodium, cesium, and francium. So once again, we're going to rank them in order of largest to smallest because it says decreasing order. So notice when we go down a group, the atomic radius increases because we have more energy levels, there's more shielding. So going down a group, the largest atom would then be francium. After francium, we have cesium as the next highest in the group. And then we have potassium as the next one on the list. And then we have sodium, followed by lithium, followed by hydrogen. So that is our order of decreasing atomic radius for elements in group 1.